morning friends, already we discussed about the stationary wave, right? Okay. Now in stationary wave the nodes and antinodes points are obtained. Therefore, how many modes of oscillation take place in particular length of a string, right? As the stationary waves are generated in the string tied at the both ends. For that purpose, the question is that the mode or the harmonic of oscillation. The system is oscillate with the whatever the harmonic or the whatever the mode of oscillation take place in a system. Right? For that purpose, the question is what is the mode or harmonic of oscillation? Explain the different mode of oscillation. That is the most important question frequently asked. And what are the equations we derive? In this case, are the most important for the objective and also the numerical. Here the different mode of oscillation, we are going to derive the equation of the frequency and wavelength. In short, we are deriving the equation of the frequency and wavelength for nth harmonic or the nth mode of oscillation. Now, what is the mode of oscillation? The system of oscillation with natural frequency is known as the normal mode of oscillation or the normal mode. Right? We are going to write down the answer of this question. The system of oscillation with natural frequency is known as normal mode. The system of oscillations with natural frequency is called normal mode. Again, the definition is that the system of oscillation with natural frequency is known as the normal. Right? What is the first harmonic? The mode of oscillation with the possible minimum natural frequency is known as the first harmonic or the fundamental harmonic. Now listen, the mode or the harmonic with possible minimum natural frequency is called first or fundamental harmonic. Or the fundamental mode. Again, the mode of the harmonic with the possible minimum natural frequency is known as the first harmonic or the first mode or the fundamental mode or the fundamental harmonics. So when the minimum possible natural frequency, the system is oscillate with this frequency, at that time the fundamental harmonic or the system is oscillate with the fundamental harmonic. Now, already we know that what is the equation of the frequency in a string time at the both wave. The equation of frequency of a stationary wave in a string tied at both ends is, we know the equation of the frequency, f is equal to nv upon 2l. L is the length of a string, v is the wave speed, and n is the mode of oscillation when n is equal to mode of oscillation v is the wave speed and L is length of a string. Length of a string. Right. From this equation, L is equal to 2NV upon 2N. That is our equation number 2. That is our equation number 1. Therefore, the length of a string required for the normal n mode of oscillation is L. We can calculate the length of a string from this equation. But we know that wave speed, so the speed of a wave v is equal to f lambda. Substitute here, therefore L is equal to n f lambda upon 2f. F cancel, therefore n lambda by 2. That is the equation of the length in terms of wavelength. Right? N lambda by 2. From this equation, the wavelength of a wave lambda is equal to 2L upon N. 2L upon N. That is our third equation. Where the N is equal to, we can take the value of different value of N. N is equal to 1, 2, 3 and so on. 1, 2, 3 and so on. Now, if N is equal to 1, N is equal to 1. Therefore, from equation 1, F1 is equal to V upon 2N. From equation 2, L is equal to either lambda by 2 or V upon 2F. From this equation, L is equal to lambda by 2 and that is the lambda 1 by 2 and lambda 1 is equal to 2N are obtained. Right? Again, as we take, if N is equal to 1, then from this equation F1 is equal to V upon 2L. Now from this equation L is equal to N lambda by 2. That means the lambda 1 by 2 and wavelength of a wave lambda 1 is equal to 2N is okay. F1 is called first harmonic or fundamental harmonic. Is known as fundamental or the first harmonic. Right? In string of length L, we obtain this term of the harmonic, fundamental harmonic. These two ends are tied at the exit support. X is equal to 0, X is equal to L. Therefore, the string is oscillate with this way. Just wait. The oscillation of a string are produced like this. Now the center point is our antinodes. The points at which the amplitude is maximum, that is known as the antinodes. So that is the fundamental mode of oscillation. Fundamental or first harmonic or the mode of oscillation. Now, as we consider n is equal to 2, if n is equal to 2, what's happened from this equation? There is the 2V F2 is equal to 2V upon 12. But V upon 12 is the F1, frequency of the first harmonic. Therefore, there is the 2F1. And thus the F2 is known as the second harmonic. And also, L is equal to 2 lambda upon 2. That means the lambda. And lambda 2 is equal to L. Lambda 2 is equal to L R of A. Thus, F2 is called second harmonic or the second mode of oscillation. Second harmonic or the second mode of oscillation. That is shown in the figure. Here the length of string is L, x is equal to L, and that is the x is equal to 0. Here the two modes of oscillation take place, therefore like this way. So this point is the that is the node, while these 2 points are antinodes. At this point, the maximum amplitude takes place. So this point is the nodes and these 2 points are the antinodes. There is the second harmonic. And as we take the F is equal to N is equal to 3. N is equal to 3. Therefore, F3 is equal to 3F1. L is equal to 2L. L is equal to 3 lambda by 2 and lambda 3 is equal to 2L by 3. 2L by 3. F3 is known as, or the F3 is called third harmonic. Third harmonic. So third harmonic are obtained in the string like this way. So here the 3 parts take place. Three times lambda by 2, because 3 times lambda by 2. So these points are the antinodes, while these points are nodes. Here there is the third harmonic. There is the third harmonic. For the third mode of oscillation. So similarly, as we take the n is equal to 4, 5, 6, so we obtain the fourth, fifth, and so on mode of oscillation or the harmonic. Right? Okay. Now listen. In a string, in general, the string is oscillate with the different mode of oscillation, or the superposition of different mode of oscillation. Right? Among them, some are strong, while some are weakly excited in the string. So here the string is oscillate with the different mode of oscillation. Among them, some oscillation take place with the some mode are strongly, while the some modes are weakly. Right? This principle of mode of oscillation is used in musical instrument like as the sitar and also the violin. Hear this? Okay. Again, what is the mode of oscillation? The system of oscillation with the natural frequency is known as the normal mode or the normal harmonics. Again, the system of oscillation with natural frequency is called the normal mode or the normal harmonics. Now, the mode or the harmonic with possible minimum natural frequency is called fundamental or the first harmonic. The equation of stationary wave in a string tied at the both ends is the equation of the frequency of stationary wave in a string tied at the both ends is f is equal to NV upon 2N. Now L is the mode of oscillation. Now V is the wave speed and L is the length of the string. So from this equation of length, L is equal to NV upon 2N. Now we know that the speed of a wave, V is equal to F lambda. Substitute in equation 2, therefore L is equal to L, instead of the V, F lambda upon 2F. F cancel, therefore N lambda by 2. So from this equation, wavelength lambda is equal to 2L upon N. There is the equation of wavelength, there is the equation of frequency, and there is the equation of length. Now, if N is equal to 1 in these three equations, so we obtain corresponding to the value of N is equal to 1, that is the F1. F1 is equal to V upon 2F. Now, L is equal to lambda by 2. Here we take the lambda 1 by 2. And lambda 1 is equal to 2F. F1 is known as the first or fundamental harmonic or the fundamental mode of oscillation. So, what are the waves are produced in a string of length L when the string is oscillate with the first harmonic? So, this type of the stationary waves are produced in a string. Okay. Yes, we take the N is equal to 2 in this three equation M, L, and L. So, we obtain F2 is equal to 2V upon 2L. But we know that V upon 2L is equal to F1. Therefore, 2F1. Now the string is oscillate with the double frequency of the fundamental frequency. Therefore, that is known as the second harmonic. For the frequency of the second harmonic, F2 is equal to double of F1. Okay. Now, L is equal to 2 lambda upon 2. 2 to cancel. Therefore, in L length of a string, one wave, saying the wavelength lambda is generated for the producer. Therefore, in L length of a string, the one complete wave, this wave, is generated. But there is the stationary wave, so this wave is reflected by Z support, so there is the reflected wave. And the wavelength lambda 2 is also the F. So here the F2 is called the second harmonic. So when the string is oscillated with the second harmonic, so what are the patterns of stationary wave generated in the string is shown in the figure. Clear this? Okay. Now, if the L is equal to 3 in this equation, therefore F is equal to 3V upon 2F. So V upon 2L is the F1, therefore 3F1. Now the equation of the length L is equal to 3V upon 2F, or L is equal to 3 lambda by 2. Therefore, in L length of a string, the 3 half wave are generated. That means the 1.5 wave are generated. That means the 3 by 2 lambda 3. And lambda 3 is equal to 12 by 3. So here the F3 is called the third harmonic, and when the string is oscillated with the third harmonic, what is the pattern of the stationary wave generate in a string that is shown in the figure. So there is the one complete wave, that means the one half wave, second half wave, and there is the third half wave. This cells reflect on the rigid support, so there is the reflected wave. So this type of the stationary wave pattern or the stationary wave is formed in a string when the string is oscillate with the third harmonic. Clear this? Very easy. Only the definition of global mode and fundamental mode or the fundamental harmonic. After that, we directly assess the equation of the frequency and wavelength of stationary wave. And we substitute the different value of n, we get the different harmonic of oscillation. Now, thus by taking the different value of n, 4, 5, 6 and so on, the different mode of harmonics are obtained. Therefore, the general equation of frequency and wavelength for nth harmonic are, we are going to return this now, taking n is equal to 4, 5, 6 and so on. The different mode of or the harmonics are obtained. The general equation of frequency and wavelength of nth harmonic is Fn is equal to Nv upon 2N is equal to Nf1, and wavelength lambda n is equal to 2N upon n. That means the lambda 1 upon n. There is the general equation of the frequency. Fn is equal to Nf1 and lambda n is equal to 2N upon n. That means the lambda 1 upon n. Right? Thus in a string, thus the string oscillates with due to the superposition of different modes with a different harmony. Among them, some are strongly, and some are weakly excited in a state. So some are the strong mode of oscillation and some are weak mode of oscillation, and due to the superposition of strong and weak different mode of oscillation, the string is oscillate. Clear this? Okay. Now, the musical instrument like as the sitar and violin. What is the use of this fundamental mode of oscillation? Musical instrument like sitar and violin. The musical instrument like as the sitar and violin are designed on this principle. Are designed on this principle. Okay. Now, just we derive the first, second, and third harmonic of oscillation. That means the string is oscillate with the first, second, and third harmonics. Now, as you take the different value of n in the equation of the frequency and wavelength, we obtain the different mode of oscillation. Like as the n is equal to 4, 5, 6, we take, right, the different mode of harmonic like as the 4th, 5th, and 6th harmonic are obtained in string. The general expression of the frequency and wavelength of nth harmonic is Fn is equal to Nv upon 12. But the V upon 12 is our F1. Therefore, n into F1. And lambda n is equal to 12 upon n. But the 12 is the lambda 1. Therefore, lambda 1 upon n. Thus, the string oscillates due to superposition of different modes. Among them, the some are strongly and some are weakly excited. Right? Okay. The musical instrument like sitar and violin are designed on this principle, on the basis of this principle. Clear this? Okay. Now, after that, we are going to discuss about the mode of oscillation in a closed pipe and also the open pipe. Right?